Today I'm going to take a little look at this static field meter. So this is a small handheld static field meter, EMIT, descoemit.com, and it does exactly what it says on the tin, which is that it measures static fields. So let me see if I can just demonstrate that to you. So first of all, we've got to zero it. Now on the back, my finger is touching a little stud, which is the earthing, and you can see that I'm grounded through this. So we push down and hold this button, and it should hopefully start counting down a little bit until it reaches 0. There we go. So we're zeroed now. Now let's pick up a bit of plastic and we'll just put the meter near it. And there we go. 1.6 kilovolts basically at a distance of 1 inch. Now there are a couple of things that I need to do to this, because as you can see it seems to work absolutely fine. Two major problems. If I turn the power off, then it just goes to that. Power off, 45. Yeah, and so I think it's kind of disconnecting part of its circuitry, but not the whole lot. And yeah, so everything is non-responsive, but of course it's still powered and still drawing current from the battery. The battery is a really tight fit. I think that the cable is actually routed out of the wrong hole, and therefore I'm not getting enough room to actually drop this in and put the lid on very neatly. It's also split out a little bit, so I need to just deal with that. And the fact that it's split out means that our targeting LEDs, which are designed to focus at a distance of 1 inch, I don't know if it's going to show in this light or not. So these two LEDs are actually turned on. Hopefully you can see that. And they should focus in and become a single dot at a distance of 1 inch, which is the measuring distance. So that's the idea. But I think that they're clearly not doing that because everything is kind of misaligned a bit. So I'm going to try and get the lid off this. That'll give us a chance to take a look, and hopefully I might be able to figure out why it doesn't turn off properly. So that was pretty straightforward. Let's take a look and see what we can see so far. Just underneath this cable tie, the battery connector, and I reckon it's supposed to go over here, actually like that, and actually sit in that space, and this wire is supposed to go the other side of that insulator, I think. Just here we've got our connector to the front panel. And, well, I may be mistaken, but it doesn't look very clever to me. Does that look like that's... I mean, this seems to have 4 connectors in it, which might be all it requires. But it seems to have a 5th down the edge that isn't finished. But that may mean nothing. I'm just seeing how this comes apart before I pull it out. And there we have it. So this is quite interesting. There's a bit more on here than I thought in some ways. I apologise, this isn't perhaps the clearest of pictures. I just grabbed this from the video stream. But anyway, let's have a quick overview of what's on the board, and then we'll actually drill down into the power section, and I want to do that of course because it won't turn off, and it's a single touch on off button. So let's work our way through, I think, generally speaking. So the first thing of note are these little pillars here. Strangely, there's one here, another one down here, and there's another one as well. Now they connect to the inside of the case, and the inside of the case is actually conductive. It's just a kind of like 200 ohms per inch, something like that, and it's connected to a stud, which in turn connects to you, and you in turn connect to ground. You can of course connect it to ground with a cable if you wish, but that's important because the whole perimeter of the board, and of course it has a ground plane on as well, connects to this just here. So this is a metal sheet that runs the whole front, across the whole front of the case, and it has 2 holes punched in it for the LEDs to shine light out of, and those 2 LEDs converge at about 1 inch away. and just here there's a small hole about 4mm drilled and about a 3mm stud just level with the surface, and it's just centered in that hole and insulated from it just by the air. So this device on the inside, so just here sort of thing, with its two legs going up, is actually the sensor. If we think about it, what we've got is the front end of this is in the electrical field, but the majority of it, this plate, is actually referenced to ground, but the stud is not referenced to ground. It's actually charged to the same voltage as the surrounding electrical field. And one of the reasons we know that is because we've got some very high resistors just here and actually on the connector here. And this isn't just a metal frame, it actually has a few components on it and some circuitry and some insulation and things. But basically it's just coupling that charge through these two wires differentially so that we can measure, because we need to get rid of RF interference and stuff. So we need to do this differentially, and we're coupling that into some op amps. So on here we've got an op amp, set of 4 op amps here, another set of 2 op amps here. Why so many op amps? Because we need to range this. We've got multiple ranges for different levels of detection. Now the charge could be positive or negative, so we also need this device up here, which is an inverter. So that takes our 5 volts that we're using for our logic and our plus 5 volts that we're using for our op amps, and it inverts it to minus 5 volts. So now we've got dual rail for our op amps, plus minus 5 volts, and everything else is referenced to ground. So that's actually pretty straightforward. That's all of our ranging and an amplification circuit, and obviously resistors for attenuation. In there's a couple of MOSFETs down here which are doing the ranging, and a bit of logic over here. I think this is used both for keyboard and for, this is an XOR gate, and I think it's just making sure that we don't get any invalid signals in or out. This here is a PIC microcontroller, so it's a PIC 16LC711. It's one-time programmable, and yeah, it's got 4 analog to digital converters on it, as you would kind of expect, and normal logic lines. Here we've got a 4 megahertz crystal. Unfortunately it's a bit overexposed. And what else have we got then? We've got another op amp here. I'm not quite sure what that's doing. It might be doing some voltage referencing and stuff like that. Unclear. Over here we've got a voltage regulator. So we've got our 9 volts comes in, goes through this device, which is the diode, and into the voltage regulator, comes out of the voltage regulator, and goes directly to the microcontroller. Wrong pin, sorry, it's that pin. And then also goes to some MOSFETs just here and here. So MOSFET here, that's for the 9 volt, and a MOSFET here, that's for the 5 volt. But note, these are on the output. Well, the 5 volt is on the output of the regulator. The regulator is permanently connected, and the microcontroller is permanently connected. Never turns off if the battery is connected. Okay, so I think that's it. Oh, what else is that? There's this big connector up here. I say big, 2.5 millimeters, and that outputs an analog signal which is 10 millivolts per kilovolt inch that has been measured. So you can connect that to a chart recorder or something like that if you wish. Yeah, that's about all she wrote. Let's take a quick look then at the power circuit. So for my not powering off side of things, I can see that my keyboard comes in and goes to the microcontroller. I can see these 2 MOSFETs up here are switching power. One is switching 9 volts, one is switching 5 volts. And they're really badly soldered and messy on the board, as are these 2 resistors nearby as well. So I think someone's had a go at those already and it hasn't solved the problem. I'm going to take those off because they look pretty disgusting, and just make sure they're okay, really. And once I've done that, then I can measure up a little bit more and trace out the circuit. There is another MOSFET just here, which I think is in the circuit as well. So tracing through, this pin here is the sort of on-off pin. It comes through picks up the end of this resistor, goes underneath this MOSFET and goes to the gate just here. And this is ground, and that's the ground connection through that MOSFET. So I'll show you that circuit in a bit more detail. First of all, let's have a look at it as a schematic, and then I'll just look at it on the board with you once I've replaced these two components. Okay, I've spent a few minutes just drawing out and tracing out the circuit around the MOSFETs, because I could see very easily we've got a diode on the end of the 9 volts, and that's feeding directly into a voltage regulator, which is essentially on all the time, and but also it's branching off. And what we've really got is a switched 9 volt circuit, which is done by this MOSFET number 1 up here, and a switched 5 volt circuit, which is done by this MOSFET number 2 down here. So M2 is switching the 5 volts, and we can show it just comes in on the source and comes out on the drain, and I've just said it's switched power going to some circuit load over here. For the 9 volts, it comes through our MOSFET, so in the source and out the drain, and yeah, and it goes to a voltage divider made up of two 10k resistors. And those are connected to the PIC microcontroller analog to digital converter 0. So it's got 4, and this is the first one of them. And that's just used to measure whether the battery is low or not. So as the voltage, all it's doing is ranging it. The analog to digital converter is about 0 to 5 volts. So this is just making sure that our battery is within that range. And it's just divided by 2. So we take our 9 volts, we divide by 2, we get about 4.5, thereabouts. And when it drops to about 3 volts or something like that, then we know the battery is pretty much expired. It's probably about 7 volts, something like that, because of the dropout in this regulator over here. So the 5 volts is very similar, we regulate it, it comes out, it goes through MOSFET 2, so in the source, out the drain, and off to the rest of the circuit, so the various operational amplifiers and things like that. Now there is another device in there which is actually mirroring that 5 volts, so you get plus minus 5 volts on your op amps. Okay, so let's take a quick look at how this circuit sort of turns on and off. So we've established that these two here, M1 and M2, the two MOSFETs, these P-channel MOSFETs, are doing the main bulk of the switching. So they've got the 9 volts and 5 volts going into them, and they're switching that on and off. So how are they kind of going about that? Well, with a P-channel MOSFET, if the gate voltage is essentially the same as the source, so in this case 9 volts or higher than the source, then actually the transistor is turned off and doesn't conduct electricity. We're just using these as switches. So this 10 meg here is making sure that the gates are pulled up towards 9 volts. Remember, these are insulated gates, and therefore there's no current flowing. So we come down here and we find the other MOSFET. So this is an N-channel MOSFET, and that works the other way around. So we can see the source is connected to ground. So if we don't put a signal onto the sort of where it says ORB0, so that's the signal from the microcontroller. If we have a 0 volt signal, so a low signal coming out of it, which is what we would have if we power it down into low power mode. We'd want that to be low, because if we don't want to turn transistors on and have power flowing, that would be silly. So we want this low. This is also pulling the gate down to 0 volts, down to ground. And so the gate's at ground. This is an N-channel MOSFET, and therefore it is not conducting electricity, because the gate and the source are both at ground. So if that isn't conducting, then essentially our gates are on M1 and M2 are just controlled by this 10 meg resistor and pulled up to a voltage where they are not allowed to conduct. So 0 volts or floating voltage on the output of the microcontroller equals all 3 transistors turned off. Now, what about the other way? If we turn the power on, so we sense the switch being pressed, the microcontroller outputs a 1 on its line. This is 10 meg, so it can easily override that. This goes to about 5 volts. So now we're 5 volts above ground, and this transistor is fully turned on. And now it's got a resistance of only a few ohms between the source and the drain. So to all effects, the gates of M1 and M2 are connected to ground. Their source is connected to considerably higher voltages, 5 and 9 volts, and that means they conduct, and therefore our power is on to our whole circuit, and off we jolly well go. So that's what's supposed to happen. Now I'm going to probe around at this junction just here, because I have replaced these two transistors. So what am I expecting? Well, let's say for example that we've got our power turned on. So if our power is turned on, this transistor is conducting, so this point here should be about 0 volts. The gates of these two transistors should be close to 0 volts if it's turned on, and they're conducting. Now it is 0 volts, so that's fine, and they are conducting. If I turn it off, however, this point here, the gates of the two MOSFETs, that should rise up to almost 9 volts. Oh no, that is interesting. In the off state, we are now at 0.023 volts. And in the on state, we're at 1.3 volts. So what could be going wrong? So I'm happy that both of these are supposed to be P channels, and I've got brand new P channel devices in there. I've put them in myself. This is a bit messy because I've resoldered that a couple of times, but it's a 10 meg. And what's happening here is I'm not getting a full range signal. I'd expect that to go sort of between 0 volt, close to 0 volts, all the way up to close to 5 volts. And I'm not getting anything like that. It's pretty much always close to 0 volts. And when I switch it off, it raises to perhaps 0.1 volts, 0.2 volts, something in that region. So that isn't elevating to where I expect. This pull-up should be pulling it up. Now these pull-ups are very big. They really don't need to be that big. You normally see large resistors like this in the standalone circuit that kind of toggles, just using an on-off switch, but no microcontroller, and that's because they're part of an RC circuit, and by putting the resistor big, basically you don't need the capacitor very big. But there is no capacitor in here. We don't need a capacitor because we're driving it from the microcontroller. So if I sort of tootle along here, follow the money, I get back to the thing that's setting that voltage is this transistor here, this MOSFET just here. So that should be pulling down to ground, or becoming a high resistance and allowing this to float. So one thing that could be wrong is that this MOSFET could be faulty, and it is actually conducting to some degree all of the time. That would be my suspicion, because after that we're in real trouble, because we just come through here, we've got a 106, which is a pull down, so that could be faulty. So essentially this microcontroller can't ever turn on this device, so that could be an issue. We can check that in a second. And of course the next thing is that we're not actually getting the output from the microcontroller, because that's all we've got. We get the output from the microcontroller through to the gate on here. This switches to ground, or doesn't switch to ground, depending whether we're turning on or off. Not this one, sorry. Bump, 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 through here. So I'm going to check this resistor, and then I'm going to replace this MOSFET and see if that solves the problem. Well, I measured that as 105 ohms. Oh boy. Let's pop him off and just see if that is 105 ohms, or whether that is, of course, could be shorting through that MOSFET just there. Tricky to get at. Okay, and that measures a good 10 meg. So we'll solder that back on in a minute or two. Yeah, and there's no shorting underneath it. And then I should be measuring, oh, not that. That is measuring 104 ohms. Okay, time for a bit of tidying up and a bit of soldering. I've got a slightly oversized soldering iron bit here really, but never mind. A bit of solder on there, a little bit on there. So I'm just turning this around and moving it away from the autofocus center just to hopefully, oops, a bit messy with that one. Okay, so I've replaced that MOSFET, the suspect one. Let's get a battery on here. And we can see there's nothing on the display at the moment. This is good news. Power on. Yes! Look at that! Power off. Fantastic. Let's have a look and see what the current draw is like now we've done that. So we are hopefully currently turned off. Okay, so that's a lot better. So that is 0.018, so 0.02 let's say. That's 20 microamps instead of 2 milliamps. So that's a significant improvement, or 18 microamps in fact. But I think that that is going to last a considerable amount of time longer. Yeah, range button works absolutely fine. Hold works. Now, I did say I thought there was a battery detection circuit in here, so if I connect this up to a power supply, you'll hopefully be able to see that. So my battery is set to 8.47 volts, and I'm just going to turn it down a little bit, down to 7.95. I'd expect about 7.2. What do we consider to be a low battery? There we go. Bat. And that is at 5.98 volts. There we go, 6.5 volts is when the battery low warning comes on. So happy with that, completely happy with that now. That is a fixed device. So now I'm just going to clean this up with a bit of alcohol just to remove the solder flux residue, reassemble it, and we'll give it a test. And so there it is, job finished, and all is well. I'm pretty happy with that. So there we have it, all done and dusted and working like a new one. So very happy with this repair. I really just wanted to fit something in because I've been working on a refurbishment of an optical attenuator, and it's a bit of a long job, and I was conscious I hadn't got anything done for a while. So here it is, and completed repair. That'll be going on my test case shelf, and I'll be using that from time to time, and happy to get it off the repair shelf. Still, hope you enjoyed that. If you did, don't forget to like the video, and of course don't forget to subscribe and also leave comments. I'll see you next time. Bye for now.